So the first tool that we've got is that we can work out how far things are away first. So that's the first thing we discovered. That we can measure the distances between objects in the universe. The next is we can work out about the physical properties of objects in the universe. And the way that we know we can do this is we can do this in the laboratory on Earth. If it works in the laboratory on Earth, it must work in the grand scheme in space. And spectroscopy uses 3 different types of spectrums, and those 3 types of spectrum can tell us a huge amount of information about an object, whether it be on Earth, in a forensic blood sample, or an unknown chemical that we discovered on the floor, or quarantine has discovered that someone is importing something and we need to know if it's talcum powder or heroin. We can work it out very, very quickly just by making it into a spectrum. Or we can use it to the furthest reaches of the galaxy. So, how do I go forward on this thing? No. Yeah. Right here. So, that last slide there was the slide just before this one starts, and that's the spectroscope. So I'm going on to this section now. And it's called the spectra of astral or celestial bodies. Astral is technically just means star-like bodies. Celestial means anything in the heavens. It doesn't really matter. Now, what you're going to be seeing here or hearing it goes directly into your workbook. So you'll need today pencils. You'll also need probably red and blue pens and some colour as well as you go through. Now, obviously, this presentation is on the Moodle, so at any stage you feel that you want to go back and revisit it, then you are welcome to do so. So, we always start with the most abundant element in the entire universe. And that element, as we know, and we've spent such a long time looking at this element, is hydrogen. Why is hydrogen such an important element in the universe? Well, we know that it's the first element created by the Big Bang after the 3 quarks got together. And therefore, it is a great indicator of what's going on in the universe. The second most common element is helium. Good. So we're going to look mostly at hydrogen because things happen with hydrogen. Now, in your book, you have this bar here. Now, unfortunately, I can't just close it all up here. I couldn't print the book in colour, otherwise it would cost a fortune. I love it. So this is what you're supposed to be seeing, this hydrogen spectrum up here. How do I go back? I don't know how I can go back. Go back, page down. Yeah. Sorry, I've got the Promethean software over top recording this. It's hard to navigate. So this is what this is representing here. But this time the UV end is down this end, and the red end will be up that end. And these black lines are the absorption. So this rectangle that you see on page 12 is a photographic spectrum, where it's you're just seeing that. So when you see this bar here, you're seeing pretending it's a continuous spectrum which has black lines. What's the name of this spectrum? An absorption. Okay. And therefore, underneath it, this would be the radiation intensity curve that comes from it. What's the other name for that? The black body radiation curve, yeah. And we know that all black bodies taper to a long, thin taper down the radio end, the red end, and they dive rapidly towards zero at the UV end. And there isn't any presence of, you can't hit an object up in the universe and get X-rays. Okay, you can only get to heat to give off UV. So that's very lucky, otherwise we'd be dying of X-rays and gamma rays. Okay, so that's the spectrum of hydrogen in the laboratory. That's the standard. The reason why it's going to be standard is we can control its purity, We can also say that it's zero, it's not moving anywhere, it's on the Earth, it's moving with us, therefore its relative speed is zero. And we can then work out exactly where each of these peaks are in wavelength. Okay? Right. Now the first spectrum that we're going to look at is the spectrum of a star, and you've already seen a few spectrums of a star. You will see where to copy it in a few moments, and I'll tell you. But a spectrum of a star, this one here, which is the UV end, by the way? Right, this end down here would be the UV end. How do I know that just by, even if I don't have any numbers down the bottom? Right, it's the deep curve. It's the deep dive to zero. This is the long tapering end on this side over here, so therefore that would be the radio end. Every time you see one of these spectrums, you need to work out which is the red and which is the blue end. Okay? This is measured in angstroms, okay, which is a very peculiar unit. It's not one of our engineering by 10 to the 9 and so on, 6, 9, 12, whatever. This is by 10 to the 10. Okay? And you already did a thing mentioning what angstroms are. It's just nanometers to 1 decimal place significance. So it doesn't matter, but these here, these 1, 2, 3, 4, you would see those as deep, dark absorption lines. And those 4 classical lines are caused by what element? Hydrogen. Why is hydrogen going to be a big feature of any star? Right, exactly. All of you are right. Because the star's made up mostly, nearly 99% of it is hydrogen, okay, as it's born. It will increase in helium as it dies, but most of it as it's born is hydrogen. Okay? So we will see these as black lines. So could I determine the temperature of this star? Yes. Okay, we just have to find, and a computer program does this quite easily. It draws a black body radiation curve across this, and you would go down. In a HSC, for instance, you would just draw the black body, and from its peak, you would do it. Okay? Sorry, I've got to touch it more forward, don't I? Okay, so this is what would be a star's absorption spectrum. This is the one that's already printed for you. So please write underneath it. This end would be what colour? UV. This end? That's the radio. This one over here would be the UV end. So make sure you label that one. Okay, so is everyone seeing where I'm writing now? It's down here. Everyone see? All the way down. Okay. Okay, now, because it's very hard on a word program to actually draw absorption spectrums, then finding these little divots going down is so hard. So can you imagine that when you're drawing this in a few more moments, that you will draw that as a divot, a trough, okay? And not like I've drawn it here. Okay? What would each of these downward, if I say peaks, downward troughs match up with? With the one above. And the depth, does the depth of the net matter at all? No, the reason why I've got them all different depths here is just to give you an idea that each of them would have a different depth, and you don't, at year 11 or year 12 high school, need to know what creates this depth. That's very, very difficult. Well, the one thing that you can tell me about the depth is it's nothing to do with how much hydrogen is present. Is that clear? Deeper those things does not tell me that there's more hydrogen than anyone else. Okay. What, do you notice that there is another element present in this spectrum? Okay, can you see there are 4 hydrogen lines? Okay, we'll have alpha 1 through alpha, beta, gamma and delta. But is there the presence of something else in the spectrum? Yes. Though you don't know it, what do you suspect that second spectrum might be? Helium, of course. Okay, so underneath you'll find 3 lines. Please don't copy this, summarise. You'll never be able to fit this into those three lines, and you'll never be able to memorise it for a HSC. Okay? So, what is characteristic about a star spectrum? Well, a star spectrum is absorption. So, it's a continuous spectrum created by the core of the star. So remember, the centre of a star, its core would create the continuous spectrum, but various frequencies and wavelengths are absorbed by what part of the star as the light comes out? Right, the corona, the photosphere, and also the outer layer, the convection and the radiative zones. So they absorb as well. But mostly, as Rebecca said, that it's the atmosphere. But the atmosphere of a star is basically what the star is made of anyway. So this process of absorption creates an absorption spectrum, and it has obvious hydrogen lines. Why are they obvious? Right, there's a lot of hydrogen and there's a lot of absorption therefore by the hydrogen. You'll find that other elements are present. Okay, and if I go back in a few more moments, which I will, you'll see that there's not just one downward trough, there's a few thousands of them, but the other one that should be present would be helium. Okay? Though helium doesn't tend to get shoved out into the corona, helium tends to get pulled down to the centre of the core by its having been more massive than hydrogen. Okay. Important statement though is the atmosphere of a star contains the same elements as the star itself because it's a big ball of gas, and as we know that the gaseous state mixes those elements up. Just going back one page, looking at the real spectrum of the star, here's a total spectrum. This one here is just a simple spectrum taken by a telescope, probably the Keck telescope in Hawaii. You'll see that there is a lot of up and down movement here. So there is a lot of other elements present, but not in really significant numbers that cause massive peaks going down. Okay? So the two elements that would definitely be present are the 4 hydrogen lines, indicating hydrogen is present, as well as maybe helium and a few other things like carbon sometimes as well. Right, the next one, the whole set of spectrums are nebulae. Nebulae just means cloud in Latin. Okay, nebula comes, also I think it comes from the Greek as well. There are different types of nebula, and I'm going to use some pictures first before we take any diagrams down. Emission nebula. Okay? Emission nebula are simply gas clouds that are contracting to create new stars and new planetary systems. As they contract, they heat up. And because they're getting hot, that's the energy of through a low density gas, it starts to give off light. Just like we were doing in our frac last time, we stimulated low density gas with electricity. This is stimulating low density gas because it's excuse me, because it's collapsing in on itself to create new stars. And this causes the nebula to glow. And because it's glowing, we can take its spectrum. If we take its spectrum, we can work out what it is made of. So that's an emission spectrum, emission nebula. And by the way, what do you reckon what spectrum you're going to get from it? Emission, okay. Yeah. It's named after the spectrum that you get. Where's my page down? Okay. So, I've already printed this black thing here to show you that it's a black background. You're going to copy the emission nebulas thing. Now, what should it look like here? Should it just be these little bars going up? No, we know that these are the peaks. So give them a little peaky look. write on your diagram, which is the red end, which is the blue end, which is the infrared, which is the radio, and so on. So you need to be able to do that because the orientation, I've deliberately made these go backwards so you get used to seeing spectrums in both orientations. So this will be the radio end down this end.
So if you're an exam, I will tell us which is
You'd normally not have to draw this. No, they don't have to. They would probably just have wavelengths down the bottom. Okay, and I would say 400 is, or 400 that means blue, 700 that means red, therefore that's blue. The other way of looking at it is which end is tapering. So here, you look at it, it's tapering that one. Okay, so most nebulae, which are clouds of gas in the universe, they're going to create more stars. So what do you reckon they're mostly made of? Like everything in the universe, what's it mostly made of? Hydrogen. So will you expect the 4 lines of hydrogen?
Yeah.
Right. The 4 lines of hydrogen, by the way, I remember are given letters of Greek, alpha, beta, gamma, and delta. And I think that's the alpha one there. It goes backward. It's blue, but anyway, who cares? So you'd get the emission of hydrogen. So it's an emission spectrum, and you'll get the 4 lines of hydrogen. Okay? Don't forget, though, that these are, we're looking only here at the visible part of our spectrum. Are the 4 lines of hydrogen also present? Are there more lines in the UV and the radio end that are associated with hydrogen? Yes, and that prac that we did the other day shows you that hydrogen is in the UV and in the infrared section. Okay, so that's not really that important. It's more the first 2 lines. So emission spectrum, because it's emission, it's gas which is glowing, it's giving off its own light, and that own light is coming from increasing heat. And it's mostly made out of hydrogen, so we expect to see very, very clearly the hydrogen lines. You don't have to call them the 4 hydrogen lines, just say the hydrogen lines. Would we expect to see anything else? Would we like to see little peaks of other things here along the way? Yes, okay. Especially if it's an exploded star which has created this nebula to create another star. So you would have other stuff in it. But what are the most 4 obvious features that you can recall for a H2C? Hydrogen. Would you expect a little presence of maybe helium? Yes, so you could say maybe helium and other elements are present at a lower level. Okay? That's what we call a band 6 response to this rather than just simply a band 4, where you say, okay, I expect to see hydrogen, and then you qualify and say, but there could be other elements at a very low trace level. Don't forget, the universe is 3/4 hydrogen, 1/4 helium, the rest trace. Okay, got that? Right, so some more pretty pictures of nebula. Remember, nebula is any cloud of gas in the universe. That was an emission nebula that you saw before. There is no difference between emission nebula and these nebulas so much, excepting, having a look at these, it's called the 3 pillars nebula. What do you reckon they're mostly made of? Hydrogen. Good, excellent, you got the right answer, because all these are mostly made of hydrogen. However, these 3 nebula also contain a significant amount of carbon. The reason being is that the gas cloud that they are up here in the tops of each of these stars that are reforming. So this used to be a massive star that's exploded, and then the gas is now recondensing to create other stars. But since it was such a massive star, the star fused hydrogen into helium and helium into carbon. So there is quite a significant amount of carbon here. When I say significant, how much do I mean? Still trace, but there's a lot more than anywhere else in the universe. And that gives it these sometimes the blackish appearance. So when we're looking at this spectrum here, would it be an emission or absorption? Emission, because it's glowing under its own accord. And we would see hydrogen as mostly present. Would we also see, because it's part of an X star, so helium?
Yeah.
Yes, and this time we're also going to see other little trace elements, little bits of carbon, nitrogen, oxygen, and especially one called titanium, which is very present in a lot of these stars. Okay. This is another type of spectrum. It's called a planetary nebula. It has nothing to do with planets. It was named, unfortunately, at the turn of the last century, when people saw these around other stars, and they thought that's where planets came from, but it's not. This is called the Eye of God nebula. It looks like it's that, but it's in reality, it's like an hourglass. It's been exploding in two directions, up and down, and it looks like that, okay, in both directions. This used to be a star in the centre here, but it's there is a very small star in the centre. But what's happening is this star is dying, and to try and avoid going supernova, it is expanding and then contracting. Every time it expands to a radius which is about the same size of Venus. Then it collapses in on itself. As it collapses in on itself, the actual every time it collapses in on itself, where the radius of the star used to be, just keeps on moving out. Okay, so you imagine a big puff of a ball of puff. As you expand out and then collapse in on yourself, this top layer keeps on moving out. And this is the top layer here. And as it goes out, it starts to cool. So it would have been white hot to begin with. And as it goes further and further out, it's starting to become red hot and then cooling to a place that we can't see. So around here is still the gas of the planetary nebula, but we aren't seeing it glow anymore because it's gone to a colder state. Are we okay with that? So planetary nebulas are created by stars that are on the verge of death. Okay? And they're avoiding they don't want to go supernova. Okay. The next one, oh, no, that's a planet, that's just to show you what they look like as a real spectrum. Okay. When you take a spectrum, like I showed you a real star spectrum a few moments ago, this is what the nebula spectrums look like. So we notice that they're typical emission spectrums. Okay. The next one are galaxies. Now, all the things that we have just been seeing, that's stars and then nebulae, they all lie within our own galaxy. In fact, they're quite close to us. Okay? A galaxy is far, far away, as it says in Star Wars. Okay? And it's a collection of thousands of stars. We cannot see single stars in this spectrum. In this picture. So when you see that star just there? Okay, that star just there. It looks like we can make that out. That star is not in that galaxy. It's in our own galaxy. It's close to us. This picture is taking it through that star field. Does that make sense? We cannot, any of the stars that you can see here, which are singles by themselves, like this one over here, they're not in this galaxy. They're in our galaxy, and they're in front of the camera. Okay? So it's like if you're trying to photograph, someone behind you doing a selfie. These are the stars that are the selfie, and the people in the distance are what we're trying to photograph. Okay? You're in the way. So that star there is not in this galaxy. It is in our galaxy. It is a star close to us. It's just in the field of view. Are we okay with that? Right. So that's the first thing we've got to remember whenever we see a picture of a galaxy like this. The second is every time you see a bright pixel, you are not seeing one star. You are probably seeing a group of about 1,000 stars. Wherever you see darkness, it doesn't mean that you are seeing no stars. It's you just can't see through the rubbish that is between you and the camera. This stuff here, this black stuff here, is junk. It is dirt. It is thick. Are we okay? So, now, this occurs in our galaxy too. If this was our galaxy, obviously it can't be because we can't take a selfie of our own galaxy. We would be out here, all the way up the corner. Okay? Now, this centre would be so bright that it would look like in the sky about 1 million of our suns. Okay? So we're out here, and if we ever turn towards the centre of our galaxy, we would be irradiated and so blinded by the light that even closing and putting your hands in front of it, you could not block the light out. But every night, the sky goes black. Isn't that lucky? The reason why we're lucky is between us, which is out here, and the centre of our galaxy, there is this type of crack, okay, that blocks the light out. If you want to see the centre of the galaxy, you can only see the light that actually gets through all this rubbish, and we call that the Milky Way. So on a really, really dark night, when you look up and you see the Milky Way, that's the centre of our galaxy. Okay? The centre of our galaxy is everyone of Sagittarian. Rightio. The centre of our galaxy lies behind the constellation of Sagittarius. And between us and that centre is a huge amount of black gas that blocks all the light from the centre of our galaxy. Luckily. Okay? Otherwise, it will be day, night, every night. Okay? So as we turn towards our sun, we would have night, and every time we turn away from our sun, we'd have day because it would be so bright. Are we okay with all this? So we're in a very, very fortunate position in our galaxy. Any closer, well, not any closer, but if we were too close right towards the centre, life could not possibly exist. Well, not life as we know it anyway. Okay? So, the first thing we've got to remember about a galaxy is we can't see any single stars, and it's a collection of thousands of stars. Okay. Now, if we can't see a single star, we can't see a spectra of a single star, so we see a collected spectrum of millions of stars. So when we see the spectrum of a galaxy, it looks like it's a spectrum of a single star, but in fact it's a combined spectrum of millions. But what we do notice is the 4 hydrogen lines, which we expect, have moved towards what end?
The red.
The red. The reason being is it's redshifted. Why is a galaxy's spectrum redshifted? Right, all galaxies are moving away from each other because this is the universal expansion. The exception for this is the close by galaxies because they are so close to us that some of them are actually coming towards us. Andromeda is an example of this, which is the largest neighbour. We will collide with Andromeda in about 200 million years. When we say collide, we'll just pass straight through each other. We won't even know we've been together. Okay? So, characteristics would be, it would have the same characteristics as a star, so therefore it would be a continuous spectrum with absorption lines, in other words known as a absorption spectrum. Good. And the hydrogen lines would be shifted towards the red end because most galaxies are moving away. However, for Andromeda, which direction would they be shifted? Towards the blue. Okay. So a very important thing to bring out here, we have brought a writing explanation. We cannot get the spectrum of a single star in another galaxy because we cannot see a single star in another galaxy. So this spectrum is a combined spectrum of thousands, if not millions, of stars. And we know that in a normal sized galaxy, in a normal sized galaxy, we can have about 400 million to up to 1 billion stars in a medium sized galaxy. In monster sized galaxies, we can have more than billions in stars. And the last thing to make sure you bring out is that most galaxies are receding from our point of view, therefore most galaxies would be receding from us. So the further the redshift, the further the galaxy would be away. What is this relationship called? Sorry? No, that causes the redshift. What's the relationship which says the further a galaxy is away from us? Yes, you've got it. Yes, it's one of the evidences.
The first one on the table with the
yes. Okay, I'll write there. Yes, it's not.
That guy.
Yes, that's the name. No, not free. Sorry? Hubble. It's called the Hubble relationship. Good. Hubble discovered that the further a galaxy was away, the faster it is receding. So we call this the Hubble redshift relationship, or the Hubble velocity distance relationship, or just the Hubble relationship. Okay, so just while you're copying that down, recapping, we've now done the spectrum of a star. We've done the spectrum of gases within our own galaxy. You can't see gas clouds in other galaxies, obviously, because they're too far away. Now we've done a spectrum of a galaxy. The next one is a very, very strange spectrum. Okay, can I move on? Okay, before I do move on, these are real spectrums from galaxies, so that you can see what they look like. Sometimes we have an emission peak, but I'm not going to try and explain that. Rightio. The last one. On the next page, you'll see quasar. Quasar stands for quasi-stellar radio sources. Okay, has everyone got it where we are? Okay. Okay, so what did you need? I said, okay, just always ask questions. What was the problem?
Oh, she thought it was meant to be an emission, but Spectra was absorption.
Oh, it's absorption. This is an emission, this one here. Yeah. Okay, now, quasars, quasi-stellar. What does the word quasi mean in English, please? It's a word. As in Quasimodo? Yes.
Like the hunchback?
Quasi-fashion or Quasimodo means quasi-fashion anyway. Quasi. No, it doesn't mean ugly. It means like. Okay? It means similar to. Okay? So you often see things around saying, okay, is this real? And there's two words that people use. Faux, for false, and quasi. Quasi is, it's nearly real. It's not totally real. It's not perfectly real, but it's close to it.
So how did they get the name Quasimodo?
Quasimodo is just Latin for, modo means fashion or of the time.
Yeah.
So quasi just means like the times. He was a person who told you about the times. Okay? So it's just a name. Okay. So quasars means quasi-stellar. So in other words, like stars, but not really stars. Radio sources. And we see them. Okay. And these sources are they are not very visible through a telescope. So this photograph here, which I'll just turn the lights off so you can see it, this is one of the few quasars that are actually visible in our telescopes. But they are very, very visible, if you say the word visible, if we use a radio telescope. Now, a radio telescope listens to radio waves. And if you were to scan across here, you'd go, Okay. Every time a radio telescope looks at a star, it picks up the radio spectrum, that tapering part, okay, and measures its intensity. This, when a radio telescope looks at this, it's not, remember, it doesn't look at the visible spectrum part, it's looking at the big taper at the end. It measures an immense, intense radio burst. So these are radio sources, radio wave sources, and when we say radio wave, it's infrared, microwaves, and radio. That's because we're talking about the radio end. And so quasars, quasi-stellar, like stars, but they are radio sources. And for a very long time, we did not know what they were or how they formed. We are still slightly not sure, but we now think that they are the first galaxies that were ever created after the Big Bang. They were so massive that all of their stars have died and then created black holes, and the gas which is inside them is now constantly falling into a black hole. So it's a massive single black hole galaxy. And as matter falls into a black hole, it emits massive amounts of X-rays. And as this is so red-shifted, and that's the reason why it looks red to us, because they are so far away, that X-rays has lengthened to the size of radio waves. So, what are they? They are massively hot. We think they are massively big black holes. And they are very far away. Because they were formed at the beginning of the universe, they are nearly 13 billion light years away, which is nearly the farthest anything can be from us. Okay? And if they are that far away, they would be receding very fast, because Hubble's relationship says the further an object is away, the faster it is travelling away from us, isn't it? So, this is what we discover is their spectrum. Firstly, it's an emission spectrum. Quasars are emitting X-rays. And those X-rays have travelled so much through space and have stretched because of the spatial expansion over time that they are now microwaves and radio waves. And where have we seen that before? What else has created a very high level wave and then it's been stretched out? Right, the cosmic background radiation has done the same thing. Okay? So, the quasi-stellar, the actual thing is, because black holes, when they swallow matter, emit gamma and X-rays, but mostly X-rays, they are now coming to us as radio waves. So they're emission spectrum. The next thing that we notice is the 4 hydrogen lines. Where are they? Right, they are so far up the red end. It's hugely red-shifted. Okay? And so we get the whole thing squashed. Where this used to be spread out along the whole thing, the red doesn't shift as much as the blue. The blue end shifts a lot and the red shifts a little bit more. So the whole thing gets concentrated. And so that's the spectrum. So we get an emission spectrum, yes?
So I mean that's the infrared and that's the...
This would be the infrared and that's the blue, yes. All of them, for all of this, the last 4 have been the same way. We've always put the red end down this way. Okay. So it's highly red-shifted and it's an emission spectrum. And the reason why we think it's this happened, because of this, we think that this is a massive black hole galaxy which is starting to collapse in on itself, create its own black holes, and therefore when that happens we'll be emitting a large amount of X-rays, and that X-rays has spread out, and as space has spread out, these X-rays are now radio waves. Okay. The last thing I want to show you is some real spectra of a quasar. This is Vega up here. This is just a star. So this is close by a star. So you can see the hydrogen alpha, beta, down and delta lines here. And this here is a quasar. It's this 3C2 quasar. And you can see that this hydrogen line, which is up this end, is now moved that far down. That doesn't look like a big shift, but remember, that's just the visible section just here. This is the full spectrum. So that's a massive shift. It's shifted it so far that it's nearly into the infrared. Okay? And this one over here, which is the delta line, is now definitely shifted into maybe the orange or the green. Okay? So it would be travelling at close to the speed of light. And that's how fast it will be receiving from us. Are we okay with that?
Yeah, with the last one that we did, when we did the graph for that, it said that it's shifting carried on a continuous basis.
Oh.
So is that the graph and then...
Yes, underneath here, it means that it's, I'll just draw it, probably the easiest way. Okay, these are the peaks here. Okay, and it's not, what it's saying is it's not coming from the zero up like that. It's got a little bit of a background. And that's probably because it's still very hot and it is glowing a bit. And we don't really know why that's happening. Okay, so you're better off just thinking it's emission. It has a small underglow of continuousness. Okay, but it's not important that. Are we okay with that? Rightio. So you should now have, the next lesson we'll go through the last section there, which takes us up to about page 21. That'll happen tomorrow. Your homework will be to make sure that you access your textbook. Has everyone got the new textbook? Okay. Does anyone have the electronic version of it?
Yeah.
Remember, it is on the Moodle. Okay, it's on, I think it's all of them. I think it's on the Space Moodle actually, where you can download this. If you didn't get that one, spectrometry on that is page 279. And well, as you read through, all I've done today is go through the different spectral types. But as of tomorrow, we will be going up through to page 289, and that will complete where we need to be. And I would have caught you up. Okay. See you later. No, I turned it off.
No, it's still not.